Welcome everybody. I'm Greg Law, co-founder and CTO at undo.io, and we're going to talk about remote collaboration and how we can actually do better than just lots of video calls. Actually, I'm in this new world in which we're all working from home. I'm joining you today from the shed in which Undo all started, which I'm now kind of come full circle to. Hopefully, we can get back into the office at some point, but not in the short term, clearly. So, what does this world all look like? Well, look, I mean, most of us, or many of us, have spent more time in the last 7 or 8 months doing this than we spent in the last sort of the previous kind of 8 years, right? And if you just look at the volume of Zoom calls, and you can apply this to whatever Google Meet and Microsoft Teams and all the rest of it, it's really gone through the roof. So this is the year we all went remote. It's also the year people learned what exponential charts really mean. So it's been a year of exponential growth in many things. But I think what you see is, what you're seeing is an acceleration of already of trends that are already well underway, and I think that it's what always happens when we do this kind of shifting from the physical world to the virtual world. The first to go at this is always kind of a lift and shift, right? Replicate in the virtual world, as closely mimic it as closely as you can as to what it was like in the physical world, and it's just never quite as good, right? The trying to recreate, simulate the any kind of simulation is not as good as the real thing. And you know how this is. I mean, there's some interesting research I saw a little while ago that even a delay of 0.2 seconds, someone asks you a question and you delay in your response of anything over 0.2 seconds, you're rated less trustworthy. And 0.2 seconds, that's pretty low latency, particularly if you're communicating across continents. We've all been there where everyone sort of starts talking at the same time and then you stop on these video calls, which, it's not like that never happens in physical world, but not nearly as much. And they're just more tiring, and everything's just not as good. And we saw this. I mean, when online retail first began, in the late 90s, there were things like virtual malls, right? People trying to almost recreate the constraints of the physical world, right? And so this is the thing: you're mimicking the physical world virtually. It's never going to be as good. If you're really good, you might get like 80%. But you can do things. You can be unshackled in the in the virtual world, and rather than trying to just make everything as good, well, let's try and do things that just don't exist in the physical. They have no analog really in the physical world, and then you can more than compensate, right? You can actually get better overall. And the big thing I think is the freedom about time. So if you're constrained to being in the same space, so you're meeting in the office, it has to be at the same time, right? You've got to be together both in time and space. But if you're going to break that constraint that you no longer need to be there at the same in the same place, then a lot of stuff you can do not being at the same time. So this is this idea of asynchronous collaboration, right? Now, asynchronous and remote collaboration, I mean, we as programmers are kind of pioneers of this. I mean, a lot of us, we prefer talking to the computer rather than people. That's kind of why we became programmers in the first place, right? And so, I mean, Slack is not just for programmers, but it was embraced first by programmers. GitHub, still is really. But these are just the latest incarnations of things that we've been doing, for years, for decades. Whether it's instant messaging or source control. I mean, even email, right, was first done by programmers just by the sort of nature of what we do. But there's a difference between the ones at the top and the ones at the bottom, and that's the sort of synchronous versus asynchronous, right? So instant messaging, as the name implies, it's a synchronous form of collaboration, and it's very good, it's useful, right? But the ability to cooperate, collaborate on source code, is something that we've figured out to do. And if you're of a certain vintage, you might have been using CVS back in the day, and it was a long way from perfect, but actually was pretty revolutionary in what it allowed us to do. Git is just the latest kind of latest version of that. And I think as well, you could also add bug trackers to these, right? Because bug trackers are not really, I mean, partly they're about just not forgetting about stuff, right? But the main thing, if you look at how people interact with bug trackers, the main thing they're doing is posting comments, right? And responding and collaborating to how often it is on on a Bugzilla or GitHub issue or your Jira ticket, you've got people claim, oh, this looks wrong. Oh no, that's you haven't quite understood. That's like that because of this, we end up with a kind of asynchronous remote collaboration to debug the code, right? And why does this matter? Why is it so important? Well, it's not just the thing on the side, right? Debugging is not just like that extra 10%. It actually dominates software development. This quote I like from Kernighan, right? You may well have heard this quote. It's quite well known, very, very sort of pithy, clever thing. And he says that everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? Now, what I think Kernighan is saying here is like give yourself margin for error, right? Understand your limitations, work, well within, because most of us are not quite as smart as we like to think we are. But I think there's a corollary of this as well, which is not quite so well understood, which is that debuggability is the limiting factor in software development, right? Because you think about what this means. There's this whatever metric for good you have in your code, whether it's how fast it runs or how quickly you can write it or how maintainable and extensible it is or how small whatever the metric for good is, if you can make your debugging twice as good, you make your code twice as good, right? It's pretty sort of profound stuff. So how that translates into the virtual world is critical, right? If we're to maintain or maybe even improve levels of productivity in software development. So we're going to see a quick demo now between my friend and colleague Jonathan, who's going to take us through how he might be looking at an issue and then how the two of us might collaborate remotely and asynchronously to get that working. So over to you, Jonathan.
So let's look at how software failure replay is used in practice, at least in a dev or test environment. This is a Jenkins pipeline. It's fairly simplified, but it's a standard checkout, run, build, run some tests. If the test pass, push to release. In this particular case, there's this extra step, which I'll talk about in a bit. This particular run is failing. It's failing some tests. So let's have a look at that. 2 passes, 4 failures. Great, can't release. So let's look at this extra step. So here we've set it up so of those tests, the 2 that passed we just skip. The 4 that failed we re-record, or we rerun under recording. And here is the bit where we're inserting a Java agent onto the Java command line to do the recording. So 4 test failures. The 4 failures are saved as Jenkins artifacts. So along with all the logs and stuff, we've got 4 recordings of those 4 test failures that we can then replay. Before we move on, let's look at another scenario. This is a different Jenkins pipeline, and this pipeline's specifically set up to capture what some people call like intermittent or flaky or fragile or sporadic test failures. It's interesting there's so many different terms for this. It's kind of a bit like dirty laundry. Nobody really wants to talk about it, but everybody has it. I've called this particular pipeline Sporadics Farm because one of our users has a setup like this that they call Sporadics Farm, and it doesn't really matter if your sporadic or intermittent failure is maybe 1 time in 10 or 1 in 100 or 1 in 1,000. It doesn't matter because this is set up to run and rerun the tests until they fail, and when they fail, a recording is generated. And if we can have a quick look at the command line for this as well. Here's our Java agent, and it's set up to save on failure. So 4 recordings generated, again saved as Jenkins artifacts. So let's take a copy of one of these or take a link. So that's recording. Now let's look at replay. So this is IntelliJ running in this case on Mac OS, and I've loaded in that recording of one of those 4 tests that came out of the Sporadics farm. and it's currently at the end of time. So what I mean is, this is pretty standard IntelliJ, but you'll notice there's this what we call timeline across the top of the screen. And think of this a bit like a skip track in a video player. And we're at the end of time, program's just exiting. So let's look up the stack. Here's our main. Let's put a breakpoint on that exit and use these extra buttons that have been added onto the IntelliJ taskbar to complement the normal buttons that allow you to go backwards in time. And I'm going to run backwards till we actually get to this point in the program's execution. Give it a minute to do that. Okay, so we've got a concurrent modification exception. These come in two flavors. There's the easy case, where you're iterating through some list and you do something stupid like add or delete through the list that you're iterating through, and you get a concurrent modification exception. That doesn't appear to be happening in this case. I think we're in the difficult case where you're iterating through a list or array, and some other thread comes in and adds or deletes from the thing that you're iterating through. Well, what do we do now? Well, first thing I can do is use IntelliJ standard exception breakpoints and add a concurrent modification exception breakpoint and run further back in time until we hit that. And this is looking for where the exception was actually generated, not where it's caught, which is what we're looking at the moment. And this fairly standard thing that you want to do when you're replaying is kind of work backwards in time and work through the logic of how we got here. So this is how we got here. We're in some standard library array list class, and it's throwing an exception. Can't really. Well, there's this background thread. What's it doing? Not much. So I don't know what's going on here. I don't really understand this bit of code. So tell you what I'll do. I'll raise a ticket. Here, so concurrent modification and spell exception in test. Let's put in a URL to the recording. But before I finish, actually, let's put a bookmark here using this bookmark feature, and so we can come back to this exactly this moment in time. And actually, you know what? I don't really understand this. Greg does. So Greg have left bookmark. Don't know this code. Right. So I'll leave that to Greg to sort out, and I'll go to bed. So this is how software failure replay works in a record time and at replay time. And I'll hand it over to Greg to handle the asynchronous collaboration.
Okay, right. Well, let's have a look at this task that Jonathan has assigned me. So I'm going to load up the recording and go to the bookmark that Jonathan placed, and we can see this concurrent modification exception. Now, you might notice if you're eagle-eyed, there's a slight line mismatch here because the source code I have on this machine where I'm replaying doesn't quite match the source code of the libraries where on the machine where the recording was taken. That's absolutely fine. You don't need to. All of that is sort of captured within the recording, and certainly if I go back to my own code, I'll be able to see it all matching up nicely. But what I can see clearly, mod count is not equal to expected mod count, right? So if I go to mod count's implementation What I want to see is where did mod count change, because that's likely to be the problem. So let's just add let's add a watch point here. So toggle field watch point like that, and reverse back to when that changed. Okay, so I'm going to click that. I've gone back in time. You can see here, look, we've gone back a little way. Again, in the system libraries, so line kind of mismatch, but if I go back into our code, I can see, oh look, here we've got an add with no kind of concurrency, no kind of locking. And interestingly, this thread look is different, right? So this thread, mutator thread, now exists. Now back when the exception was caught, the thread had terminated by that point, right? So it wasn't in the list, but I've gone back to when the modification happened by this offending thread. And I can see this is Jonathan's code here, where he's done this without any kind of locking. So I'm just going to add another bookmark like that. I'm going to save this recording out, send it back to Jonathan, slap him on the wrists appropriately, and have him go fix his code. Okay, so there we see a nice example of how we can use software failure replay and time travel debugging to do some sort of next level asynchronous collaboration to debug, in this case, relatively straightforward issue, but you can see how that would apply to really right through to really complex and nasty problems. Let's take a step back and let's look at this in the wider context. So let's go right back to the beginning, and as many people know, the term debugging was created by Grace Hopper when she found an actual physical bug inside the machine causing a problem, right? Actually not true. So this is sort of widely misunderstood. And if you look at here's the notebook, the logbook from Grace Hopper, and she says here, this is the first actual case of a bug being found, right? So you wouldn't think about it, you wouldn't use language like that. Clearly it's a joke, and you wouldn't use jokey language like that if the term wasn't already in widespread use. In fact, it predates programming. There are references to it found in Edison's logbooks. But it was really when we started programming a lot that the term really became widely used, right? And it's bugs and debugging are almost now synonymous with programming. And I think fundamentally because it turns out that human beings just aren't really built for programming, right? The level of precision that's needed just isn't a very human thing, right? And if you think about this, I mean, even I'd like to rate myself as a fairly okay programmer. How many lines of code can I typically write and have it work first time? I mean, even if I'm really trying, like what, 40 maybe, if I'm lucky. In practice, it never works first time, right? And this is sort of all part of, as I was saying before, how debugging dominates software development. And if you think about that for a moment, especially on modern systems, I mean, it really is, talk about needle in a haystack. It really is quite amazing that we debug anything at all. A single thread on a single node is in a single process is often going to be issuing billions of instructions every second. Scale that up, multiple threads, multiple processes collaborating across the network to get the job done. Yeah, I mean, how do we actually, the fact that humans can make this stuff work at all is quite surprising. And of course we have to use different tools as well as techniques to do that. And that's where my interest in this really comes from. And I think the tooling that we have to understand what software is really doing, I think is just fundamental to how far and how quickly we can progress as an industry. So yeah, understanding what software is really doing, that's really what debugging is, right? It's figuring out what happened. I had some expectations. I expected my program to do something and something else happened. And now I need to figure out what's the root cause of that difference. Where did reality diverge from my expectations, right? Billions of operations every second, that's often really hard to do. And in fact, the longer it is between the root cause, the bug itself, the failure to take a lock, or the off by one error, or whatever it is, the longer that elapses between that and the effects manifesting themselves, right? The exception, the unhandled exception, the assertion failing, the program generating bad output, whatever, the longer that gap is, then clearly the much harder it is to find out what the root cause is. And then the other thing is the repeatability, right? So how does it fail the same way every time? Because if it does, I can just run it a whole bunch of times, and every time I run it, I tease out a little bit more information. But if it only fails one time in 100 or one time in 1,000, or when it does fail, it fails in a different way, then that gets really, really hard, right? It's how I get the information out that I need, how I extract the signal from this noise, if you like. And of course, life gets really interesting when you have those issues in the top right-hand corner there, where they're both a long time, a long time between root cause and effect, and a sort of unrepeatable, non-deterministic world. And that clearly is where software failure replay really comes into its own at that point, right? I mean, it's very useful, I think, for all bugs, even the simplest. But for once you get used to it, it just becomes a way that's just like in fact, one of our customers referred to it recently as like having superpowers, which I quite liked. And so it's useful even for the most trivial of issues. But when you get into that top right hand corner, then it really comes into its own. And I think it's an idea whose time has come, and we're seeing more and more of it now. And I think, like so many things in this pandemic world that we're living in, trends that were already happening are being accelerated, and I think software failure replay is no exception to that. So we've just looked at Live Recorder for Java. There's Live Recorder for C++ and Go as well, and also actually Rust and some other languages. There's a kind of similar technology on Linux called RR, stands for Record and Replay. It's very cool stuff. Works very well. A little bit constrained in where it can work, but if it can work on your system, then it's pretty good. And there's also inbuilt into GDB, although that is pretty slow. So I'm not sure that really counts as a kind of appropriate for debugging complex systems at scale, but nonetheless it's there and it works. Out on Windows, and Microsoft are getting into this in quite a big way, right? So the time travel debugging in Visual Studio is now a kind of a real thing, both on C++ and on C#. And there's a startup company called RevDebug doing some interesting stuff as well. There's also web, JavaScript and web application debugging and replay from replay.io and Mozilla. Actually, Mozilla started the RR project as well, so they're kind of into all this in quite a big way. So there's a lot of this stuff coming along, although it's not really new. It's not a new idea for sure. There have been research papers on this going back to the 1970s, countless PhD projects. But if we have a look at kind of why it's hard, you might see why it's taken the industry a little while to get to the point where it really is becoming deployed on real world systems. So as I said earlier, debugging is what happened, right? Another way of asking the same question is, what was the previous state and the state before that and the state before that? And certainly if I want to do some time travel debugging and I want to step back in time, right, then I'm going to need to know what the state was at the previous line, etc. And that's harder than you might think, right? When the machine is executing, it's actually destroying information as it goes. So somehow we need to reconstruct it. Really, there's two ways we can try and do that. One is just to save it, right? Every time we modify some piece of state, we save what the preceding state was, and we generate a log that we can then unwind. Works, can be effective, but the trouble is the logs get really big really fast, right? Because once again, billions of operations a second, every single one changing some state, because if you think about it, that means it's in a tight infinite loop. So every single one is changing some state, and that's just a lot of stuff to save. So the other way to do it is to recompute what the preceding state was. But that is not as straightforward as you might think, right? So if we think about a simple case statement like this, where we increment A, well, that's pretty easy to recompute if we're looking at the state of the machine after that line of code is executed, and we want to say what was the state of A before, pretty straightforward, right? But most statements aren't like that. Most statements look maybe like this. What was the value of A prior to this? If I know the value of this statement is executed, I know the value of A and B equals to the same. What value was A prior to that statement? That information is gone, right? And you can't just you can't play computers back. Actually, there's some interesting research now beginning to develop in making reversible logic, so that you can actually run programs backwards, run computers backwards, and that turns out to be interesting also from an energy point of view, because there's when you get down to the sort of quantum level, there's a very direct link between energy and information. And if you destroy information, then that consumes energy, right? And that causes that basically results in heat. So if we can make a computer that doesn't destroy information and that can actually reverse, it turns out they can, in principle at least, be very energy efficient. But that's all. It's all very interesting stuff. But that is all years and decades away. Very very nascent kind of research. For the world today, running on commodity hardware, computers do not run backwards, and we cannot just unpick these. So if we're going to recompute the state, though, we can do it in a different way, which is to start at the beginning and basically replay that program. So let's say my program is done. Let's say my program has executed 1,000 operations, 1,000 lines of code. Let's say I want to go back one line. Well, I could go back to the beginning and play it forwards 999 lines, right? And then that's effectively as though I've stepped back. And in fact, in the demo that you just saw, that's exactly what was happening behind the scenes. When the reverse button is clicked, the thing goes away, finds a preceding snapshot, runs that forward. Okay, so we don't have to run forward right from the beginning. We can keep snapshots. We can make them copy on write, so they're nice and efficient. As far as the user's concerned, it's kind of pretty instantaneous. But in reality, we're saving much less state. We're actually recomputing the majority of the state that we look at. Now, this only works if we can ensure that the re-execution happens exactly the same as the reference recording, right, as the first time round. And if the program is something like, say it's a compiler, and I can arrange to feed it the same inputs the same source files each time, then I can kind of do that. But if it's most programs have some kind of non-deterministic inputs, and even then I better be sure I've got my my exact same source that I'm running against. So what we want to do actually is capture all of the non-deterministic inputs, and when we replay those, we synthesize those non-deterministic operations. So for example, if you're reading off the network, when we're recording, you record the bytes that were read off of the network. When you're replaying from that snapshot, you don't actually touch the network at all. You just insert those bytes from the event log back into the program execution. So it's kind of simulating all the I/O, and that goes for any system, any I/O with the system or with a human. It goes for any thread scheduling, timing differences that might happen. It goes for accesses to shared memory, shared with a device or shared with another process. Anything that might cause the same run of the program to behave differently. But those tend to be a tiny fraction of everything that the computer is doing, right? A really, really small percentage of those billions of operations. And so if we do that, exactly how much memory we need, how much event log we need to record does vary from program to program, of course. Depends how much non-deterministic stuff the program is doing. But a few megabytes per second is kind of typical, right? And so you can see how at that scale, you can then and you can have a circular event log, so the old stuff falls off the back. So you can record big large systems for a long time with that kind of performance. So just to summarize then, I mean, I think the key takeaway really at the wider level is, don't fall into that trap that people often do when they're trying to virtualize something. They simulate the physical world as best they could, and it should be really no surprise that it kind of doesn't work very well, because the physical world, when we do, humans have even evolved to work together and be social groups in the physical world, right? I mean, and we've certainly optimized all of our processes and practices very tightly over millennia or millions of years. So to expect you can just replace that in the virtual world and it be as good is pretty optimistic, to say the least. And so instead, work out what you can do in the virtual world that you cannot do in the physical world. And I think one of the biggest things there is that we're if you're no longer constrained to being in the same space, then you don't need to be in the same time. Combine that with this fact that debugging completely dominates software development, and you can see how if you want to be a highly effective remote software development team, then you have to figure out how to do your debugging through remote collaboration and critically exploit that asynchronous advantage that you can get. And that's really what software failure replay, time travel debugging absolutely excels at. So that's it. Thank you for listening. I think we're going to Q&A now.